These gold and pink motifs are striking, but their true complexity lies in their resilience. This color fastness is engineered to last generations without fading. Achieving that level of permanent color at an industrial scale today relies heavily on highly toxic synthetic chemistry. The linear supply chains of modern manufacturing dump millions of gallons of runoff into natural rivers, poisoning local water supplies to maintain high production speeds. Yet artisans in India achieved identical, permanent color fastness for thousands of years using biodegradable organic inputs. Instead of forcing reactions with harsh catalysts, these traditional methods rely on specific physical processes, natural airflow, and precise timing. How did these ancient artisans lock pigment into fabric so permanently, using only plants and minerals? ethnoSTEAM treats traditional indigenous crafts as rigorous empirical frameworks of science and engineering. The primary engineering challenge happens at the molecular level. Raw cellulose, the main component of cotton, completely repels water-based organic pigments. To understand how they solved this, we must reverse engineer two steps: the extraction of raw organic colorants and the surface chemistry of mordants. Validating these techniques preserves cultural heritage while building a scalable template for modern green manufacturing. The first step in this chemical process is sourcing the dye. Rather than synthesizing colors from petroleum, artisans isolate organic pigments directly from local biomass. The Botanical weaver dyers of Odisha extract deep reds and blacks using the roots of the Aal plant. On the Andhra coast, the pinkish red found in kalamkari textiles is derived from the Chayaveru plant. Modern iterations of this extraction actively upcycle materials that would otherwise end up in landfills. Eco-conscious dyers now harvest floral waste from temple ceremonies, alongside agricultural byproducts like pomegranate rinds and guava leaves. Artisans filter, mix, and boil these raw materials to ensure they are engineered into viable liquid pigments. This phase establishes a zero-waste, bio-based chemical supply chain that rivals the vibrancy of synthetic production. Having the pigment is only half the battle. If applied directly to plant-based fibers like cotton, most natural extracts remain fugitive. Organic dyes bind easily to protein-based animal fibers like wool, but they lack the chemical affinity to adhere to the cellulose in plant fibers. At the molecular scale, there is no structural bond holding a natural dye molecule to a raw cotton fiber. When water hits the fabric, the pigment washes away, leaving the cotton bare. Without an engineered intervention to alter the surface chemistry of the cotton, organic dyes cannot achieve permanent results. The ancient solution to this bond failure is a chemical process known as mordanting. A mordant is an inorganic oxide that acts as a permanent chemical bridge between the cellulose fiber and the dye molecule. The most critical mordant used in these textiles is potassium aluminum sulfate, or alum. Before dyeing, the fabric is treated so the alum molecules penetrate the porous structure of the cellulose fiber. Inside the cellulose, the alum acts as a Lewis acid, making it receptive to accepting electrons. When the electron-rich natural dye molecule is introduced, it is immediately drawn to the alum. They react to form rigid coordinate bonds. The dye, the alum, and the cellulose lock together into an insoluble structure called a lake complex. Engineering this specific coordination complex guarantees industrial-grade fastness using only natural elements. Translating that microscopic chemistry into production requires macroscopic workflows, seen in traditional frameworks like Tellier-Rumal and Adrak. It begins with the hard day process, where fabrics are soaked in tamarind seed powder to prime the surface for the mordant. For complex patterns, artisans apply a resist paste, like the clay and gum mixture called dabu, to block dye penetration in targeted areas. After applying the mordant, the fabric must rest for 24 hours to allow those coordinate bonds to fully solidify. Once the bonds are set, the fabric undergoes mechanical washing and drying, utilizing the open air and sunlight. This process operates at a scale that allows for processing long sheets of fabric simultaneously, without grid power. Contrast this with modern synthetic dye houses, which require industrial boilers and electrical heat to force pigment fixation. These physical, time-based steps substitute for toxic industrial catalysts. Modern fast fashion relies on a linear sequence: extract raw resources, apply toxic dyes, and discard the waste. The ethnoSTEAM model is circular. The cycle begins with organic fiber farming, moves through the upcycling of agricultural waste for color, and uses natural minerals for mordanting. The system also features an end-of-life upcycling node, seen in the traditional kantha quilt. Women artisans layer discarded saris and bind them together using thread drawn from the old fabric borders, ensuring zero textile waste. This closed-loop architecture aligns with the United Nations Sustainable Development Goal for responsible consumption and production. As we look to detoxify global manufacturing, the ethnoSTEAM framework proves that high-performance green chemistry has already been engineered and perfected over millennia.